on to our next test. We're going to learn. So we're learning this one. We have a 1.6, which is going to be ratio under tomorrow. It's going to wrap off the whole techniques. So we're going to do this one for now. It's called alternating series. Now, alternating series. What do we mean by alternating series? When we talk about alternating series, we're talking about a series which looks like -1 to the n times an. Okay, so you have some an where all its terms are positive, and then you just have this -1 to the n, maybe it's -1 to the n minus 1, doesn't matter. But this is an alternating series. What an alternating series is like? You have -1 to the n times some positive terms, right? And so what this is going to end up doing to us, what this is going to end up giving us, is we're going to end up having this. Again, maybe I'll write it together or it's the same thing. It just starts off with right. But we're going to have kind of these alternating terms where one's positive, one's negative, one's positive, one's negative, one's positive, one's negative. So now, so in this case, what would happen is we get, since the -1 to the n minus 1 there, we'd end up having a1, right? Because you'd have 1 minus 1, which is 0, -0, 1, times an, so it'd be a1, but then we get minus a2, plus a3, minus a4, plus a5, minus a6, plus blah, blah, blah. Okay? So each time you're flipping the sign of your term. Okay? And again, we really, I mean, there's some cases where we've kind of addressed it a little bit, but this is going to be the big one where we really kind of tie all these together. Because in some ways, these series are really easy to work with. They don't really take much effort out of us at all. Because what sort of ends up happening is that these terms end up just kind of taking a piece out of each other each time. So instead of like having to continuously add positive pieces, you just keep subtracting off parts until you just kind of get to a point where you're like, well, I'm not subtracting much anymore. And that's going to lead us to what's called, so if I have a series like this, we can use the test that's called the alternating series test. Okay, alternating series test. What do we do with this? Okay, so if the alternating series and I'm gonna write it as a book has it. They use n equals 1 to infinity, and they're gonna have -1 to the n minus 1 times. You can use a and you can use b, and I think they use bn just because we like to take the whole thing as an, but again, it doesn't matter what the letter you use. It's just be consistent. And then this is the same thing as b1 minus b2 plus b3 minus b4. But if this satisfies two conditions, again, satisfies two conditions. The first of which being that the limit as n approaches infinity of bn equals 0. That's the first condition. And the second condition, which is like it, is going to be that b of n plus 1 is less than or equal to b of n for all n. Okay, then series is convergent. Okay, so if we want to determine whether an alternating series like this converges, we only have to test two things. We have to say first, or one, we have to say, does the limit of that bn term go to 0? And two, is bn plus 1 less than or equal to bn for all n? Okay, now, I'll be honest with you. I don't completely get this one, because if this is true, then this should also be true by extension. Otherwise, it wouldn't really make sense. Now, there is the case to be argued that you might have, it might still go to 0 all the way towards infinity, but there might still be some points like in the middle where it kind of goes up. You might want to be suspicious. So we still want to include it as a condition, just to be careful, but really this should, if you see this, then hopefully this will come through as well. Obviously we need to check. So these are our conditions. That's what we're going to be checking for. Okay. There's a proof for this in the book. I'm not going to do it again because, or not again. On Monday, we talked about this idea of like monotonic sequences, kind of having bounds on them, which I kind of had left this thing on the board here at the end. And that's used to say that since there's a bound, then there's going to be sort of a convergence for the sums. I'm going to spare you for that. Although there is precedent to say that this does make sense. As long as it satisfies these two conditions, it works out. Despite normally on the last few years, it's that if the limit goes to 0, then that doesn't necessarily mean it converges, but that's actually one of the big those work. Okay, questions? Or we just do some samples of this? No. Okay. Good. Well, let's just start with a very interesting example, which is going to be okay. Does this series converge or diverge? This one diverges, and this one's by p series. Okay. -1. What do we do? -1. What do you think about this one? So all I did was put a -1 to the -1 on it. Do you think this is going to converge or diverge? A little hard to tell, maybe. No. You would think at first that it might diverge because the other one diverges. So why would adding the -1? But we again, I said to trust me on this, but there is a proof to show this test is true. So we can use this test on this function to see if it converges or diverges. Right? So the first condition, we're just going to see if I take the limit and then approaches infinity of 1 over n, if it goes to 0. Is that true? Yes, good. Okay. Second, we need to see if b of n plus 1 is less than or equal to b of n for all n. Right? So b of n plus 1 is just going to be 1 over n plus 1. And then b of n is going to be 1 over n. So is this true? Is 1 over n plus 1 always less than or equal to 1 over n? At least for our numbers, right? Of course, I know negative numbers exist, so there might be a weird, but we're just talking about 1, 2, 3, 4, 5, 6. So that's absolutely okay. So, based on alternating series test, what does it say about this function? Is it convergent or divergent? It's convergent. That's it. You don't have to follow that one. Or you mean like find the sum or something? Yeah. Or no. In most of the cases we've done, like the problems we've done so far, you can't really find the sum. Like you can estimate it if you go a long ways, but we don't have any solve it to find it. There is actually a way to solve this one. This is the nice one. We actually do have the value for this. If you're curious, this is the natural log too. Funny enough. But in general, we don't have ways to find this. So, this is really all the section boils down to. I'll do some more examples, and there's like a little, kind of an approximating sort of detail I want to add on at the end. But when we're talking about alternating series, something that, well, actually, maybe I should say that. But it is a little odd, right? To consider that if I just have 1 over n, it diverges, but if I put a -1 on it, it converges. Okay, we're gonna run in. There's gonna be, and there's an existence of like the long series that act like that, where they don't work typically, but the -1 does. But even with the -1, there's a lot of weird things that happen. Like if I just decide, so, you know, this sum typically would look like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, right? But for some reason, if I decided that I didn't like adding them this way, and instead I wanted to do 1 plus 1/3, and then subtract 1/2, and then subtract 1/4, and then add 1/5, and add 1/7, like do 2 odds, 2 evens, 2 odds, 2 even. I'd still be adding all the same things, but this sum would actually be different. The value would end up being different. So again, I'll talk about that a bit more tomorrow, but just sort of something to think about. Of like that, this seems odd. You know, when can we? You know, when does it? When does changing the order change the sum? When is there cases where it doesn't change the sum at all? Like what's that really happening? Cool. Any questions for me at the moment before we move on? Just to a couple more examples. Nope. Okay. Cool. So let's still do we'll do the first one. That's here. I'll just do it. Space wouldn't be that much. We're gonna look at the sum, and we'll do from n equals 0 to infinity of -1 to the n plus 1 over the square root of n. So I want to determine if this converges or diverges. Okay. Question: is this an alternating series? Yes. It has a -1 on it. -1 to the power, so that means it's definitely a alternating series. Does that make sense? If it has a -1 to the n on it, that makes it an alternating series. It's alternating signs. Okay. So since it's an alternating series, I can just use these two conditions. Okay. So we're going to look at the first one. We're going to take the limit, it's in approach to infinity of what's Bn in this case. Okay, what's the limit of that? 0. You have 1 over infinity essentially, so that's just 0. Okay. 2 is, so we have 1 over the square root of n plus 1 plus 1, right? And we're wanting to make sure that this is always less than or equal to 1 over square root of n plus 1. So maybe I'll just write this as 1 over the square root. Right? We want to show that Bn plus 1 is less than or equal to Bn. Is that true? Yes. Right? N plus 2 is bigger than n plus 1. So that means that this denominator is bigger, which means the number is smaller. That's it. Okay. Is it convergent or divergent? It's convergent. All right, AST. Okay. Raise your hand if you think this is difficult. Okay. No, okay. I trust you guys can do this. It should be fairly straightforward, right? You just you say, does it have a -1 on it? Okay, that's an alternating series. Is the limit 0? Okay, good. Do the two terms compare correctly? Yes, they do. Okay. Good. So let's do another one. Okay, let's go. All right, we're gonna do the sum from n equals 1 to infinity of -1 to the n times n squared over n squared plus n plus 1. Okay. Question. Is that an alternating series? Okay, why? Oh, that's -1 to the n. Good. It's an alternating series. Okay. Can I use alternating series test? Yes, we can, because it's an alternating series. Okay. So we need to see if it satisfies the first condition. So we're going to take the limit as n approaches infinity of n squared over n squared plus n plus 1. What's that limit? Okay. Is that 0? Okay. So I mean, it's a converge or diverge? It diverges. Please, questions for me at all on this? Okay. Yes.
Doesn't matter if you conduct the divergence test, right? It doesn't matter if you like.
Well, it's not quite the divergence test. The divergence test is technically, this should be like it should be positive term. It doesn't matter too much, but it's in a way, yes, it is. But that -1 here, it's the limit not being 0, like, or the limit being 0 doesn't say anything about being divergent. This one does. So there's a little bit more at stake, I guess. Or I guess more stake with this one versus that one. Like, in a way. It's just one of the conditions here. So it is the same, but which makes it nice though, because you're like, oh, it's an alternating. Let me just see if it goes to 0 first. Okay, and then you just kind of check the other condition. But as I said, this condition should follow pretty straightforward from this one as long as this works. But I want you to show that this still works. And that would make sense. Okay, so I want to see that. Okay, again, if you just write this for me, and you don't, I mean, if you want to explain yourself, that's fine, but, well, actually, I feel like I'm gonna end up having some people just write it and be like, oh, sure, it works. Maybe, so if you want to give a little bit of justification, just say the non-configured here, and that's it, but, yeah. For sure. Any other questions? Okay, let me do, okay, let's do number 16. We're gonna do n equals 1 to infinity of n times the cosine of n pi all over 2 to the n. Okay. This one looks kind of funny. It doesn't look like an alternating series at the very first, like just by looking at it. Well, let's kind of plug in some terms. Let's plug in some numbers into that cosine part, right? What is the cosine of? What's the cosine of pi? what's the cosine of, so we plug in 2 pi. Cosine of 3 pi. 4 pi would be 1, 5 pi would be -1, 6 pi would be 1, 7 pi would be -1. So this is actually the same thing as this series. Okay, it's just written a little stranger, right? But plugging in those natural numbers gives you the same, right? You get -1 then 1 then -1 then 1. So it's -1 to the end. Okay, so they might try to throw you off, but it's still the same thing, right? Now that's definitely an alternating series. Right? So what do I do with an alternating series? We use what test? The alternating series test. Yes. Good. Okay. So condition 1, the limit as n approaches infinity of n over 2 to the n. What do we think? Does that go to 0? Couple ways to do it. Again, you could just say, well, the bottom grows faster, or we could say use L'Hopital's rule. If I use L'Hopital's rule, I get 1 over 2 to the n times natural log of 2. But that would just end up being 0. Make sense? Is that good there? That's going to be 0. Again, 2 to the n grows way faster than this. Okay, and then condition 2, we want to see that n plus, so we want to say that n plus 1 over 2 to the n plus 1 is going to be smaller than n over 2 to the n. This one's not as obvious. I mean, you could plug in numbers and see, but I can't just make a straightforward conclusion to say, oh, well, yeah, of course it's smaller. Like we don't know. So here's what we might be able to do, right? If we're unsure, if I can't really show 100% sure in this case of what's going to happen, okay? If I wanted to know, right? Because what we want to show is that thing's going to decrease as the numbers get bigger, right? Do we know something that tells us if a function is going to increase or decrease? Do we have some tool that can tell us about increasing, decreasing thing? The first derivative. Okay. So I'm going to look at the function in x over 2 to the x. So I just replace the n with the x instead. Okay. Now let's take the derivative of this thing. What rule do I need to use to take the derivative of this? Quotient rule. Okay. So what's quotient rule going to look like in this case? What's going to be on top? So we're going to have
1, 2, 3.
good. So we take the bottom times the derivative of the top. So we have 2 to the x times 1 minus top times the derivative of the bottom. What's the derivative of the bottom? Right. For those of you who kept your formula sheets, you can test pull them out. You might want to pull them out and see if look at the formula here, right? We learned this one in chapter 6, right? If I have 2 to a power, or I have anything to a power, I just write it down again, and then I multiply by natural log of 2. Okay, it's just, remember the derivative of e to the x is e to the x. The derivative of a number to the x is a number to the x times the natural log of that number. Okay, well, in these cases it'd be 1. That would just be 1. We get 2x and 4. Okay, and this is all over 2 to the x squared. Okay, now what will be of interest to me is to see what the critical points are. Right? So I'm going to take this, I'm going to set it equal to 0. Okay, is this thing gonna be zero if the denominator is equal to zero? No, it would be undefined. I wanna see what, and the bottom can't be zero anyway. I need to see when the numerator is equal to zero. So I'm gonna have. Now, do these two terms have anything in common with each other? 2 to the x. So I'm gonna factor that out. I'm gonna be left with 1 minus x times the natural log of 2. That equals 0. Okay. This can't be 0, right? I can't take 2 to any power and get 0. But the inside can be 0. What is x gonna be in that case? Good. Fantastic. So, one of our natural logs. Now, feel free if you want to put that into a calculator source, right? Just to make sure what the number is going to be. This is approximately because natural log of 2 is about 0.69, 0.693. So about I'll say like 0.7. So 1 over 0.7. It's going to be I'll say it's probably somewhere around 1.3, right? So it's a little bit above, right? So that's our critical point, right? Our only critical point. And now we kind of want to see what happens on either side, right? Although we're not as interested as much on the left side, we're more interested to see what happens when the numbers get bigger than that, right? 2, 3, 4, 5, 6, 7, etc. Right? So what's going to happen if I plug in? So we have 1.3. Right? What's an easy number bigger than 2? Yeah, 2, right? So I'm going to take 2 and plug it in. So I'm going to get 2 to the second power, or I can even plug it into the speed right here. So we get 1 minus 2 times the natural log of 2, which, again, natural log of 2 is going to be approximately 0.693. So if I multiply that by 2, is that bigger or smaller than 1? So 2 times 0.693, is that bigger or smaller than 1? It's bigger, right? That's going to put you over the 1, so that's bigger. So this part is negative, and this piece is positive. So, and maybe we'll so 1 over ln2. So when we plugged in 2, we said that this part's negative, so it's decreasing over here. And then you could test this side of be increasing. Well, I guess you could plug in a lot of A, but it's increasing and then decreasing, right? But this is the more important side. So, and that includes 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to the end. Okay, so this relationship is going to be true for all except one value. Which is what? Right? We said this is about 1.3, right? So what number isn't included over on the side that we want? 1. Okay, interesting. What do you think that means? Any guesses? Like I'm really I just want us to think about this, right? Let's think through it, right? Is that a problem? Is that one being missing? Is that going to be a problem? Right? So everything's fine if 2 and on, right? So let me ask this question. If I start at 2 instead, would that be convergent? Yeah, because it definitely satisfies everything, right? Okay. But the original series I had is just that. plus you plug in 1 in here. What do I get when I plug 1 into this? I get 1 plus this thing, right? So you get -1 times 1, so -1 over 2 to the 1, which is 2. We said this is converging or diverging. This is converging. Right, again, because this relationship is true, we took a little bit of a longer route to show that with the derivative, but it's true, but it's only true for when we start at 2 and on, right? But if I plug 1 in there to add that extra term, it just gives a -1/2. Now, if I have a convergent sum, which is so some finite number, and I add -1 to it, is that somehow going to become infinity or not exist? No. So the sum of convergence. Yes.
I was gonna ask, because, you made it equal to 5 to minus 1/2. Right? Or-
You can do -1/2 to the end, yeah.
Yeah, so, that was what I was confused, because, you know, you can't have it equal. But you.
Yeah. Yeah, so it's the equivalent sum, right? So all that to say, there's a little bit of an asterisk on that, okay? We're all in after maybe some starting point, right? So if the first two don't work, right? Like if I have, so in this case, if I plug 1 into this, it's not gonna be true. 1/2 is gonna be bigger than 2 over, well, I guess it might be. Let's think about that. That'd be 2 over 4. Oh, it's equal. Well, it's equal to that. So it actually still doesn't work. But all those extra terms are really good. Like if it's just a couple terms that are off and everything else is true, then that's okay, right? The scope here is just to say, if I keep going, this is gonna happen. I'm not gonna get this, right? Where one term's here, and then 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 one term's here, right? Where it's always changing, right? But if I have like this, then I can make it. Okay? So, again, I don't expect me to go put anything too crazy like this, but I want you guys to think about the problem, and sometimes you're gonna have to put a little bit more effort into working through it than just saying, oh, it just works, right? We need to make sure that everything comes together well. So, questions for me at all on that? Okay. Last thing I'll mention is, so the question, there was a question asked earlier about, well, so can I find the sum of that thing now? That most of these sums we can't evaluate. It's gonna be important to know if they converge, right? So we can actually, our approximations mean something, but I can't just like automatically know the sum of these cases. However, we have ways to estimate our sums, right? So to say, basically to say, okay, I will add this many terms together. And then once I reach this point, right, once I reach like the 7th term, the 7th term is only going to add like 0.02, 0.00002 to it. So like everything after that's only going to add that much. And so it's not really going to change very much after that. So those first 2 terms are all I need. Okay, we can use that. So we have a little theorem here, which I'll write down for us in these last few minutes, which says if S is equal to the sum of -1 to the n minus one, b to the n, where b to the n is greater than 0, where b to the n is greater than 0, if s is greater than 0, something might be a typo. Is, so it says where b in is greater than 0 is the sum of an alternating series which satisfies two conditions, so 1 and 2. Okay, then I'm gonna write this thing called Rn, okay, of the remainder of my actual sum is equal to the sum minus kind of this Sn, remember Sn is like our partial sum up to n, and this is gonna be less than or equal to b to the n plus 1. Okay, so what does this mean? So essentially, all we're saying here is that if I have a sum, if I have an alternating series sum, okay, where b ends always greater than 0, we want positive terms here, and it satisfies 1 and 2, then the remainder between the partial sum and the actual sum, right, this Rn, is going to be less than or equal to the b of n plus 1 term, right? So they give an example. They take the sum. They're looking at a series which has a factorial in it. 1 over n factorial, and then it has -1 to the n to the b minus 1. Oh, this are 0. 0 and -1 to the n. Okay, yeah. So they have this series, and they say, okay, let me just evaluate some term, right? So I'm gonna plug in 0, I get 1 over 0 factorial. Anybody, what's 0 factorial gonna be? Not 0, actually. What is it? 1. Okay. If you want a reason for that, just look at the other ones. Right, 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 2 times 1, etc. Each time when I go down a level, I divide by that factorial number, right? So to go from 3 factorial to 2 factorial, I divide by 2. To go from 2 factorial to 1 factorial, I divide by 2. And to go from 1 factorial to 0 factorial, I divide by 1. So there's a few little proofs to show that. So we get 1 over 1 minus 1 over 1, so that would actually cancel, but I'll just continue a few more terms. We'd have 1 plus 1 over 2 minus 1 over 6 plus dot, and then it goes to, it adds the 6th term, which is going to be plus 1 over 6 factorial, which is going to be 720, and then it stops at the term when we put 7, which is like 5,040. Okay, so at this point, you're kind of getting to a point where you're like, oh, I don't want to keep evaluating this. Those are getting too big. Can I just stop? Can I just get the estimate? And what you're going to find is you can't, because, or like say it's going to be really close. Because what we can do is I can take this number, right, and I can see what the remainder looks like. So I'm going to use. So R6 essentially, so I'll write this in here. R6 is going to be less than or equal to B of n plus 1, which is B7. But B7 is 1 over 5,040. Now, 1 over 5,040 is approximately going to be approximately 0.001 0.00019-ish. Alright, so again, this is the remainder. This is the difference, approximately the difference between my actual sum and the partial sum that I did, right? So there's so many zeros, like, this is really close. So I do not need to go there. I can just stop at the first few terms you called, okay? So this is kind of just taking, I can't get the exact number, but I can get a really good idea. Okay, again, don't expect anything, I can't really give you too much like this on a test if you want people to, it's gonna be a bad estimation, by example, but, that's it. Okay, any other questions for me regarding that at all? No? Okay, well, that's it. You can, feel free to go, I'll stick around if you have any questions. Just please don't, be afraid of. I know this example looks harder, it's really not that difficult. Just really try to grasp onto this and do that. Most of the examples should be really straightforward, okay?